In the last video, I went over some definitions for this unit to review from Chem 1, molarity, dilution, standard solutions, looking at the concentration of different ions in a solution. And we talked about the different formulas, but I ran out of time, so I wanted to go through an example calculation for each of those terms that we talked about in the last video. And there you will have some more on your problem set, and I'll be happy to go through as many other examples as you need me to in class. But I just wanted to go through a few just to refresh your memory on how to do these calculations. And so if you look at the first one, calculate the molarity of 11.5 gram copper 2 chloride dissolved in 275 milliliters of water. So I'm going to look at the fact that I have 11.5 grams of copper 2 chloride, and I'm going to set the molarity, which is what I'm trying to solve for, times, change this into liters, so 0.2500 liters. And then, as a reminder from the last video, if molarity times volume is on the top, then 1 is going to go on the bottom, and we're not dealing with a chemical reaction, so there's no coefficients that we need to worry about. And then if grams is on the top, I'm going to put formula weight on the bottom, and the formula weight for calcium 2 chloride is 134.45. And then just cross multiply. For sig figs, 11.5 has 3, 250.0 has 4, so your answer should have 3. So 0.342 molar is the molarity for that particular solution. All right, so for question 2, what would be the concentration of each ion in the solution? Now this is looking at ion concentration, which we didn't do a lot of in Chem 1, but it's not that difficult. It's just looking at your solution and trying to figure out what the mole ratio is for each ion compared to the whole solution. And so if we look at copper 2 chloride, and as this dissociates into water, it's going to break apart into copper and 2 chloride ions. So what these coefficients tell you is that for every 1 copper ion, there's going to be 2 chloride ions, or another way of putting that is the concentration of the chloride ions is going to be double whatever the concentration of the copper ions are, because I'm just looking at the coefficients. The ratio is 1 to 2. Now, if I compare copper chloride to just copper, their coefficients are the same, which means their mole ratio is the same. And so if you have 0.342 as the concentration for the whole solution, because the mole ratio of the copper ions to the whole solution is the same, they're going to have the same concentration. Now, if we look at the mole ratio again of the copper to the chloride, it's a 1 to 2. And so if the concentration of the copper ions is 0.342, the chloride ions are going to be double. And so it's going to be 0.684. Now you can think about this just looking at mole ratio like I did, doubling it, halving it, that sort of thing. Or if it makes more sense to you to set up a stoichiometry proportion, you can do that as well. And so if you have 0.342 is the molarity of the whole solution, and we're dealing with a 250 milliliter solution, you're going to put 1 on the bottom. And now I'm going to introduce the coefficient for this balanced dissociation reaction. So that's a 1, and I'm solving for X molarity of, let me just put the unit on that so we know what we're talking about. So X molarity of, let's do the copper ions first. And then it's still the same solution, so the volume is still the same. And on the bottom, it's going to be 1 times copper's coefficient, which is 1. And so if you do this cross multiplication, you get the same number. Now, if I were to look at the chlorine, the left side of this proportion is going to be the same, but now I'm looking at the molarity of the chlorine ions. Well, the coefficient in this balanced dissociation reaction is 2, So on the bottom, you're going to get a 2. And now if you cross multiply, you get the double the amount. So again, you can just look at it and sort of instinctively know I'm going to double this, I'm going to half this. These are going to be the same because the coefficients are the same. And if that makes sense to you, that's fine. But if you need to set up a proportion to do it and solve it using stoichiometry, what we've been doing, then that's fine too. Just know that the coefficients at the bottom are going to be the coefficients from the dissociation reaction. So you may need to either write out the dissociation reaction if that's helpful for you, or at least think about it in your head because you need to know what your coefficients are going to be. And again, we will do more of those in class and you'll have more on the upcoming problem set, but I just wanted to show you at least one example so you have it in your notes and you can reference it if you need to in the future. All right, next one. What mass of solid copper chloride should be obtained from evaporating 20 milliliters of the solution above? So we're using this molarity that we've been solving, we've been using, and so we're trying to find mass. Remember, mass is always grams. And I know the coefficient, or excuse me, I know the formula weight from example 1. So 134.45. And the molarity, it's the same molarity that we've been using. But now we've evaporated, and so we have 20 milliliters, which is 0.02 liters. And 1 goes on the bottom. And so what this question is saying is if you took this 250 milliliters of the solution and took 20 milliliters out of it and then evaporated it, how much of this evaporated the water, how much salt would be left? And so if we do this calculation and we look at our sig figs, we're still with 3. And so you have 0.920 grams of the copper chloride salt. And so there would be approximately 1 gram of the salt from that 20 milliliters of solution. Right. And the last example, how much water would need to be added to 20 milliliters of the above solution to reduce the concentration to 0.25. And so this is a dilution question. And so we're going to use M1V1. Let me rewrite that so it's a little bit more legible. M1V1 is equal to M2V2. Now remember, your 1s are before the dilution and your 2s are after the dilution. And so before the dilution, the molarity of the solution was 0.342. And the volume, it says here, how much would we need to be added to the 20 milliliters? So it says we're using 20 milliliters. Now, mathematically speaking, it's not going to matter if you use milliliters on both sides or liters on both sides because they cancel out in the end. But just to stick with the consistency with what we're doing and always converting things to liters, I'm going to convert to liters. And so the molarity that we're trying to get to is 0.25. Now, we are solving for volume 2 because I need to know what the final volume is in order to figure out how much water I have to add to the initial volume to get to the final. And so if I do this calculation, you end up getting 0.02736 liters. Now I've carried more sig figs than I need, but that's because I'm in the middle of a question. And just to remind us, we're using 3, and so this is where we would be. Now to figure out how much water needs to be added, you're going to take volume 2 and subtract volume 1. And I'm going to convert it back to milliliters just because it's easier for me to subtract. And so your volume 2 is going to be 27.36. And again, here's the sig fig that we're looking at. And you're going to subtract 20 milliliters. So if I subtract this, you get 7.36 milliliters. Now, looking at sig figs, as a reminder, when you are subtracting, or adding, you're going to look at the number of significant figures after the decimal point. And so 20.0 has 1 after the decimal point. And if we're looking at the 3 sig figs from the multiplication before, we're also looking at 1 number after the decimal point. And so this final answer should actually be rounded to 7.4 milliliters. So that means you need to add 7.4 milliliters of water to that initial solution in order to dilute it to 0.250. So that was an example of a molarity calculation looking at the concentration of different ions in a solution. This is another molarity kind of thing, but going backwards, looking at grams. And this one is a dilution. And you will have some of those in the problem set. You'll also have some solution stoichiometry thrown into the problem set, which is the exact same formula, same calculations. The only thing to remember when you're dealing with stoichiometry, because you have a balanced equation, you need to be looking at those coefficients like we did up here. So make sure you have a balanced equation. The last thing I'm going to show you is this is just sort of a step-by-step for those of you who much prefer to have a list of steps to follow for each question. So this is kind of guiding you through how to do these reactions or how to do these problems. Hopefully this is something that if it hasn't already become second nature, it does by the end of this unit, because stoichiometry should be engraved in your brain from as much as we did it in Chem 1, but for those of you who are still a little bit rusty or need some more practice, this step-by-step should help you with how to solve any of these stoichiometry solutions, or in this case, precipitation reaction questions. Now, I understand some of these steps can be combined, which is fine, but this is just sort of an outline for those of you who might need some refresher. And here is the next problem set of all the things that I reviewed. It's problem set 12. And you will have time in class to work on it, but if you have some time and you want to get started, there is the problem set for this section of the notes that we reviewed from Chem 1 material. And that's it.